Hey everyone, so in this tutorial I'm going to be taking you through how to do reverse cyclic pushovers in OpenSees. We're also going to look at some of the different integrator types you can use and the advantages and disadvantages to each of them. We're going to be looking at a simple cantilever concrete beam. We're going to be applying some sort of force to the top of this, and we're going to end up with some sort of force displacement hysteresis like we've seen on the right. The concrete beam is going to be the same beam that I looked at in the original pushover analysis, and there's going to be a few small tweaks to it to make it a little bit more exciting. So, looking at what I'm going to go over, I'm going to give a quick introduction to the problem. I'm going to go over what reverse cyclic analysis is, why it's different, and then I'm going to overview some of the integrators. Then I'm going to take you into the code, and so we're going to overview the structure of the project, and then I'm going to do a line-by-line breakdown of the code and kind of giving you an explanation of why I'm doing what I'm doing. Basically, this is what we're looking at. So we have some sort of simple concrete beam. There's going to be 3 nodes in the problem. I was using force beam columns before to capture the nonlinearity. This concrete section looks like this. I've kind of changed it from the past concrete section in that I have made this, this spacing is 75 everywhere, but I've also made it asymmetrical. So that will make conversions just a little bit harder to figure out, and it'll make our hysteresis look a little bit more interesting. So yeah, that's what we're looking at. Generally, I'll just take you through an overview of like the project structure. As I said, we're going to be doing 3 different types of integration methods. I talked a little bit about displacement and load control in the last video. We'll be looking at all 3 of those. In this one, I'm also going to add in the Arclength control, just for fun. So looking at reverse cyclic analyses and integrators, basically, when you're doing a reverse cyclic analysis, you're taking your model and you're applying some sort of displacement to that model, and that displacement is repeating, or it is reversing, so we're going to have a directionality to the load. We're not just applying it in one direction, it's repeating, or reversing rather. It will be defined with a load protocol. You should have an idea of what load protocol you are using. There's a whole bunch of specifications out there on what to use. There are different ones for, say, like concrete walls, wood walls, CLT walls. It will really depend and vary quite a bit from problem. But the important thing is this will have a set amplitude in a number of cycles. And this is what we'll be applying to our structure. So you'll want to start with this. You'll generally have this being applied as a time series, but it will depend on the integrator that you use, and we'll get into that in a bit. Generally, what you're using is you'll either use a load control, a displacement control, or Arclength control integrator. And so the big thing that really sets apart these reverse cyclic analyses is, well, as always, we need to watch out for areas of big changes. That's where we're going to have our convergence problems in the model. But one big thing is because our load is not reversing, these reversal points are going to be very significant. And we're going to have to be a little bit careful of how we increment the load near them. Of course, these other 2, so say you might have problems with initial loading or points of big nonlinearity in a standard pushover model, but for reverse cyclic, these kind of reversal points are going to be potentially big points of pain. And also sometimes you might have issues when you're passing through zero in terms of big stiffness changes. It's not as frequent, but just something to potentially keep an eye on. Um, so some strategies that we can use to help us here. There's a bunch of fancy things we could do in OpenSees, but it all, at the end of the day, comes down to we want to increment our load much more slowly near these points of big stiffness changes. And in particular, we know there will always be big stiffness changes at the reversal points. So generally, one strategy that I've found pretty successful, that has been fairly successful for me, is to have a smaller load incrementation near these reversal points. And here I'm showing something that's on the order, this is maybe like a fifth of what's below. You can go pretty small here. You could say do like increments that are like 1/100th of the, say, the typical load incrementation. But I've generally had success implementing this just in my time series. So when I create my time series as it goes from step 1 to 2 to 3, I can, near these reversal points, I'll actually have a much smaller incrementation of the load in that time series. I've generally found this to be a pretty simple and straightforward way of implementing these smaller time steps and getting good results. You could do some fancier things in OpenSees though. You could try and say like read the displacement, and once you start getting close to your reversal point, you could start slowing down the load incrementation. That's a little bit more advanced, and I haven't necessarily done that as much or haven't had as much success doing that. But it is something that you could do if you really wanted to. Okay, so getting into the load control algorithms, or excuse me, the integrators and what they are. The first one we're talking about is load control. And this is a bit of a misnomer. Really, in OpenSees, this is a pseudo time control. So we're gonna go. What the thing that we're controlling is the pseudo time. So we're going from some time 1 to time 2, and then the forces are scaling. This one is nice. It's easy to understand. When you're doing reverse cyclic pushovers, what you'll normally do is you will apply some displacement to your model, and then you'll control that displacement using the time series. And yeah, so this as a load control, you are doing Newton Raphson iterations. So, your iterations will look something like that maybe. And as we go from step 1, to step 2, we'll have some sort of load in the model. Note that this is not necessarily increasing. If this is, say, step 1, step 2, oh, that's grade 2, isn't it? Ugh, oh well. We'll live with it. 1, 2, and then 3. You might, if you're controlling the displacements, this doesn't necessarily have to be higher. We could end up with a load 4 that's down here if we're iterating the displacements with our load control algorithm. That is a little bit unintuitive. If you know the theory of behind load control, generally what we call load control is something where just purely the force in the model is changing. Like this is the dF. What's going on in OpenSees is a little bit different than that, but just know that we can actually capture this kind of downwards behavior with a load control algorithm in OpenSees, as long as we're doing applying displacements. And again, this is because what's happening is really load control is pseudo time control, and we're going from one time step to the next time step. Okay, the next integrator is the displacement control integrator. So this one behaves a little bit more like, I would say, the theory behind a displacement control. The big difference here is OpenSees is now fully in control of the load factor. So what we do in this algorithm is we tell OpenSees, okay, I want some du in the model at some degree of freedom. So imagine our cantilever. We'll tell it what node we want it at. So we'd say node 3 and then the degree of freedom. And then we'll specify, by specifying du, assuming we have some loads here, or displacements, OpenSees will figure out how to scale the load factor such that the new displacement in the model is equal to this change du. So again, the big difference here logistically is we're not dealing with a time series anymore. We're going to be telling the model to change the displacement by a certain amount, and then OpenSees will handle the internals of changing this load factor. And this is a pretty robust way of doing iterations in that it is displacement control. We don't have to worry about ending up with a force that's too big in the model. We can just apply straight up forces to the model and as opposed to displacements, and OpenSees will figure out how to scale those forces. Because we're in displacement control, we're doing displacement control iterations. So these look kind of funky, but they'll be about this line. So we'll always be iterating to this line and to this point. And then the last thing to consider about this is the thing that we actually input to OpenSees is the load protocol, or rather a backbone of it. And I'll get into that once we look at the code example. So finally, the Arclength control method. This is really, it's like load control, but iterations are occurring in Arc. So we tell OpenSees, okay, we want to iterate along a arc of a certain length. So there's going to be some radius, say like dr, and then the iterations will occur along basically this curve. So it's a little bit more robust from a load control algorithm in that we can capture a lot more behavior in theory. And in theory, it's the type of iteration that has the least number of restrictions. If you say had some crazy curve like this, you know, which is probably never going to have a curve like this for like a real structure, but you know, just pretending that you did, you wouldn't necessarily be able to capture this with a load control or displacement control algorithm, but you could capture this with an Arclength control algorithm. In practice, I've found it quite finicky. I found that you need really small time steps to converge, especially near these reversal points. So there's just something to keep in mind. Generally, when I am doing my analyses, I would say I'm not using load control. Excuse me, I'm not using Arclength control. I'm just using load control or displacement control. And I would say this is generally something that you don't need to know about unless you, for some reason, have a really complicated problem with lots of nonlinearity. Then it might help you out. But yeah, that will be the background. Next, we're going to get into an overview of the code. So yeah, I'll get that going and stay with me. So now we can get into the actual fun stuff, which is a summary of the folder structure. Maybe not as fun, but then the actual code itself. I've broken things down into a set of folders. So I have a documentation folder. This is everything that keeps track of our actual model itself. Functions folder. So this will this will have like the Python files that are common to all of the analyses. We'll see that in a bit. The outputs folder and the load protocols folder. So I'll start with these just because they're the most straightforward, and then we'll actually get into, once we look at code, then we can go into the functions themselves. So in documentation, I have this model overview folder, basically in Excel, that will let me track what's going on in the model. I've kind of gone a little bit light on this model because it's so simple. You know, no location, coordinates, section geometry, so this helps us keep track of like where the fibers are in the one section that we have, and materials. If I had a bigger model, I would really break this down. I would say like have a layout of like nodes and node connectivity per floor. I might have like a breakdown of the material, the nonlinear properties of each material. That might sound a little bit like overkill, and I know this is probably boring to a lot of people, but the reality is when you're working with OpenSees, it's really hard to understand what's going on in your model. It's not like eTabs where you can just look at it, see a nice user interface, and have a really slick overview of it. Really, you have to manage a lot of this stuff yourself. So although it's probably not as fun as you would want it to be, I think it's a really good idea to have a pretty rigorous documentation process of what's going on in your model. And it will really help you, at least it's helped me as I'm building my model. Just having this documentation helps me organize in my mind how I want to program the structure. So that's documentation. Not very sexy, but I think important. And I have these tutorial resources. This is just for me. This is everything that is actually going into the tutorial you're watching right now. So again, I like to organize it and have it all in the same spot. So outputs, this is again pretty simple. For each of the for each of the analyses, you'll see just a folder that will be a dump for the data that we want to come out of it. Load protocols is also simple. I have a bunch of load protocols in this folder, and then the analysis files will read from them. And oh yeah, one thing to note here, I'm using this THF file. I actually don't, I have no clue why this is the extension that is used. These are basically text files. Like you can open this up with Notepad++, and this is all like just straight up text. I think maybe for load protocols, this might be standard. Maybe there's like some program that reads these and puts them in an actuator or something. I'm not sure, but just know this, you can use whatever you want. These can be text files, but I've seen THF for some reason used quite a bit. Okay, great. Now we'll get into the actual files and the program itself. So yeah, I'll start with the displacement. Actually, no, start with load control. That would be simplest. So if we look at our load analysis, the way it starts, I'm importing OpenSees. I'm importing NumPy. I actually don't need to do that, but there's a chance that, I don't know, NumPy gets used so often. I'll just leave it. And then I'm importing a whole bunch of functions here. So the model functions, analysis functions, recorder functions, plot functions. So these are pretty similar to what was used in prior tutorials, so I won't go too deep into them. But I think the thing that's really important is if we look at, say, like our displacement analysis, we're importing the same set of functions here. And this is really, really important. You want to be using a common set of functions to build your model, to introspect your model. So like say record or like get outputs from your model in like plots. It's pretty important to do that. You don't want to have like a whole bunch of, like if you look at these analyses types, you don't want to be using a different analysis, or you don't want this to be tied to the analysis. You just want one set of functions that apply everywhere. If you do that, your life will be so much easier. You have to change code in much less places, and it will be great. So these functions are linked to the functions folder. And one thing I'm doing is I'm actually using, so I have this empty init like Python file. You'll see this is completely empty. But what this does is it tells Python that this is a package. So it makes the functions folder a package, and then because it's a package, we can import the functions from this lower folder. And so let's start model functions. Again, I'm going to go over this pretty quickly because I've gone over this in prior tutorials. But starting, we import some, or excuse me, we set some units. This get sections is basically what we're using to define the materials in the model, the model itself, and the sections. So I'm making a steel material, a flexible material, and a rigid material. This is just something I do for diagnostic purposes. We define a steel O2 material. Again, this is just pretty standard properties for steel O2. Maybe this post-yield stiffness is a little bit low, but yeah, pretty standard properties for a concrete material. I'm not a big concrete person, so these may or may not be totally accurate, but yeah, nonlinear concrete materials. We define our section and its vertices, and we'll do that in a loop. And one thing that I'm doing that's different than my prior tutorial is I have set the rebar to be asymmetrical, and I've done that just by taking out one of the rebar layers. All this is pretty straightforward. We define a number of like XY coordinates for the rebar, and then we define a fiber section that has the appropriate number of fibers. So again, we only need one in the Z direction, and we're using 100. In the Y direction, we define the rebar fibers, and there's two here. I believe one, oh yeah, so one is just an elastic one, and one is a nonlinear one. And then we define two section properties as well. So pretty straightforward, not a lot of changes here. The actual building model is identical to what it was before. So we're using force beam columns, and I won't get too into this, but yeah, fixing the bottom node. And so, yeah, that's that. Plot functions, this is the same as before, really. I've changed, so what this is doing is reading data from the outputs folder and making a plot of it. So pretty straightforward. We tell it what, we construct basically the folder that we want it to look at. So this base name is going to be the path to this folder, and then including the name of the analysis, and then these like the displacements and reactions will be defined based on this base name, like this. We use NumPy to read the files, and then we just make a plot. Pretty simple stuff. What is going on with, so the caveat is these have been set before in the recorders functions, so maybe we'll look at that now. In the recorder functions, we're doing a similar thing where we define the base name. So this will be the path to the folder that we look at. So again, we're just constructing, we want it to go to outputs, the directory name, so this will be dynamic. We'll pass that in. And then the analysis name also will be dynamic. And this lets us reuse the same function for all of the analysis types. This is way better than hard coding the variable. And yeah, they're kind of linked. One thing I don't love is right now you'll see this base name is kind of defined twice between the two files. so if we changed where we wanted to store the files, we would have to change 2 separate lines of code. That's not ideal, but for such a small thing, I think it's fine. So we've looked at those 2 sets of functions. The analysis functions is now what we'll get into, and we'll do that at the same time as we look at the actual analyses themselves. So going back to the load analysis, we've imported our functions, and again, we'll get into analysis in a bit, but we're defining some variables. We're defining the output name, so load control of displacement. This again is what we're going to pass to our recorder and plot functions, and you can see we do this down here. And the analysis is really simple. We build the model, so we build the materials, build the model. We run the analysis using our cyclic analysis, and I'll get into that. And then we plot it. So this is a similar structure. You're going to note displacement analysis is a little bit different in that here we're defining a load protocol and passing that to the analysis. But everything, again, same functions between the two. So that's really great. Taking a look at the analysis, or we'll start down here. So in the analysis functions, if we go up, I've left, so there's the load control of force, load control of the displacement. Those 2 are the same as from before, but now I've added this cyclic analysis with load control. So you'll see the first thing we have, we're passing a maximum displacement. So this will run until it reaches that maximum displacement. And we're giving it a file name for the time series. So looking, and by the way, with my protocols, I've made a few different ones depending on time steps. So you'll see here the different sizes. Basically, the smaller, this just corresponds to how big the time steps are between the 2. So here I was only using the small one, and let's just see. So yeah, this is about so in the order of like 0.1 or 0.001, so about 1 millimeter between each step. It does vary a little bit for these initial ones, but I think, yeah, if we go down, yeah, that's about what we're looking at. So about 1 millimeter. And that's the input load protocol that we're applying to it. Again, this load protocol is specific to the problem, but we go through, we define the control node. So the control node, this is the top one. Control degree of freedom is 1, so in the x direction, and du is 0.01. So we're using this, the initial thing that we apply to the model is going to be this single degree of freedom constraint in terms of deflection. So we define these time series and then the single degree of freedom constraint. This is 1, so the time series will completely scale up or down the loads based on just the displacement. So basically whatever is in this time series, that is going to be applied directly to the model. And I define this step size, so yeah, so it looks like I'm not using a full step size. I'm not, like, you could have this as 1, and then if it was 1 from step to step, 1 just means that we're going from this one to this one in a full step. What I have is 0.1 there, so basically we're linearly interpolating between the 2 and going 0.1 of the way between the 2 points. So we're using a little bit smaller the time step, and then these are pretty standard, band, general, plane, whatever, don't need to get into that. But you see we have the integrator, and I'm actually using some of the options that are available to the load control. We tell it what step size. I tell it 1 iteration, but I also allow it to increase the step size. So this basically, I have it so that we can use 100 times the standard step size, and this will let us run a little bit quicker for areas where we are converging really nicely. So yeah, I'm just giving it this range. I could give it a smaller number here for the minimum step size, but I'm pretty happy with this. And then, yeah, standard convergence test. And then we get into our analysis loop. I'm just doing some documenting here. So n will be the number of times it runs the analysis. I'm also, it looks like I'm recording the time and then the load factor at each time. So this could be useful for diagnostic purposes. We analyze in a loop as before, so while it's less than the max displacement, we're going to iterate through and run analysis. If the analysis fails, we're going to go into our analysis loop, and this is the same as before. So basically it just tries smaller time steps, goes through, and then at the end it tries a few things like more load iterations and trying a modified Newton. And then very important, at the end of this, we set it back to the original test and integrator that was used. So yeah, if we go back, that is the load control with displacement. So I'll just run, actually no, I'll run them all at the end so you can see the results. But yeah. Then next I'll overview the displacement control analysis. So this one, as I said, is a little bit different. We're using the same functions as before, but we're defining this load protocol. And this load protocol is basically, if we were to look in one of these files, it is the peak values for the, the peak values from the file. So if you look here, we actually break up, the load. You can see it starts increasing to a certain number, to its peak, and then decreasing, it goes negative. But we have all the actual points. Like this is the time steps that we want OpenSees to analyze. Displacement control, we don't do that. We just tell it the end result, the like the peak value we want to go to we want it to go to. In this case, so you can see 0.0015, the peak number that's about here, and then you'll see the negative down here. So that is what we're giving it, and then with our code, we're going to be controlling how it runs the displacements. And we're telling it the number of repeats it wants. That's basically like if we wanted to go to this, twice or 3 times, we can control that here. All the functions are the same, except for now we're doing cyclic. We have the cyclic analysis. I've also commented out, I do have this displacement control with force if I just wanted to run like a straight up pushover. I still have that in there, but commented out. Yeah, so we'll take a look at this function. So I've given us some standard variables. Probably don't need to do this. Like I probably should just have it look like this, and in fact that won't change the behavior, but I'll just leave it. This is basically the load protocol, so the values we want it to cycle to, the repeats, and then dx is the increment that we want at each step. So I'm using 0.0001, so 0.1 millimeters. At each step, it's going to try and get that displacement. All of this stuff is pretty similar, except so like we define the control node and the control degree of freedom. That's the same. We're applying a force to the model. This is what's going to get scaled up or down. OpenSees will figure out what load factor to scale in order to get our displacement that we want. And then we actually can give it a constant time series. So this is kind of neat because OpenSees is figuring out all the stuff in the back end. We only need a constant time series. OpenSees does all the logistics, and then plane load pattern with the force in the degree of freedom that we want. All of this stuff is the same, except for you'll notice we don't define our integrator here. We'll actually define our integrator within the analysis loop down here. So our analysis loop will start, and basically we'll iterate through the load protocol itself now. So X is the value in the load protocol that we want. So if we go back, X would be 0.15 first, and then this would be the second one. And then number of repeats will be this variable. So they're all 3. So it will be like 1.5 millimeters and 3 repeats. And then, yeah, so like we begin by getting the values. We then go into the number of cycles. So because we're repeating that many cycles, we iterate 1 to however many we want. Here's where actually we define the integrator. So that's, again, a little bit different from what we're doing before. We say displacement control, and actually we can take out these two, but we call it displacement control, the degree of freedom, and then this is the target step. So this is the initial step. The number of iterations that we allow to complete. This isn't too important. We could give it 1, we could give it 10. This is basically sub-iterations that it's doing for each step. And then we give it a minimum and we give it a maximum. And this is kind of a nice feature in that we get a lot of control even before we get to the analysis loop. We can let OpenSees control how big and how small it wants the step to be. So that's kind of nice. Then in the inner loop, so obviously we have our analysis. We will run an analysis loop that is a displacement control analysis loop. And then if that fails, we'll end the analysis. So the displacement control loop is similar to the load control loop. And I'll just minimize this. Basically, we're telling it to run smaller step sizes in the model. And again, very similar. We define the integrator. We're going down to 1,000 times. And then at the end, we'll try modified Newton Raphson with a lower convergence criteria and 200 iterations. So, yeah, so that's what the analysis loop looks like for displacement. Another thing that's quite different is we run the positive cycle. So this, again, this is incrementing. We'll do dx, 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 dx until we get to where we want. Once we get there, we will actually increment backwards. And to do that, we create the displacement control integrator, but we use negative values. So now instead of positive dx, we're using negative dx. We're using, so like the minimum step size and maximum step size has changed. And we're going to integrate until it is less than the current breakpoint. So the analysis is the same, but basically this, if we think of our cyclic analysis, this will get us up to the peak point, and this will reverse us from the peak point to the negative peak point. Then we finish it, and then we run again. So, we might go from 0 to 1.5 mils, back to negative 1.5 mils down here. Then we're done. We iterate back to the number of cycles, and then we run this again. So from negative 1.5 to 1. And we keep doing that until we're done the number of cycles we need. And then once we get there, we'll iterate to the next thing in the load protocol. So in this case, we would iterate to 2.2 millimeters. And then we do that for the whole load control algorithm. So again, this is quite a bit different than what we saw before, but a little bit nicer in that we don't have to actually construct the load protocol in a file. We can just give it these displacements and tell it what dx we want and let it go off to the races. And then finally, the arc length control. So this is all very similar to what we saw before. I'll walk you through. So we have this pushover arc. Because I haven't walked you through this in a prior video, we'll just look at this really quickly. This is all the same. We're using a displacement control, we're applying a displacement to the model, and then we're using a linear load control. So for the pushover, this arc is just going to increase constantly from time step to time step, and then we're also going to all of this is the same as load control, except for we have we're defining the arc length. And so with arc length, there is kind of two factors to it. There's the actual arc length itself, and there's a scaling factor. Unless you really know what you're doing, just set this to 0. For almost everything, 0 is an appropriate number. And then darc is going to be the change in the arc length that we want to look at each step as we do the iterations. So in this case, I'm using an arc length of 0.01 meters, so 1 millimeter. And you can use larger or smaller. In this case, because it's just a pushover, I'm using a pretty big one just to get it going a little bit faster. So that's the pushover arc length. The cyclic analysis of arc length, again, this is pretty similar to the load protocol one. We have some sort of maximum displacement, and then we have some sort of arc length that we want to use. You're going to notice this is way smaller. When I went through and did this analysis, I found that the arc length method converged much more slowly. It was a lot more finicky to make work, basically. So I had to use both the smaller load protocol with smaller time steps there and a really small arc length. This was really driven by the reversal points. So at the reversal points, it was really struggling to converge, but everywhere else it was fine. So there might be a really smart way of setting a small arc length for those issue points. I haven't quite found something that works out perfectly yet. I found that the analysis loop, even though we're setting a smaller one, once it gets to those reversal points, it seems to still struggle a little bit there. But so this is the arc length. Again, we're defining arc length integrator. We're using that factor of 0. And we have this arc length analysis loop. Again, this is really similar to our other analysis loops. We're just taking the arc length. We're trying a smaller size at each step, and then trying to run again. So you can see I try some ridiculously small arc length sizes, and that seemed to be needed to get the analysis over some of these tricky reversal points. Yeah, so that is the arc length control method. So I'll just quickly run some of these now so we can just see what it looks like. You'll notice, and actually I'll go to displacement control because this is the one that runs fastest. So you can see I'm actually printing each of the load protocol points too, and that's kind of a nice thing to see. It lets us know that our analysis is actually doing something. So you can see we're printing them out, and then that's what's going on here. I will run load control as well, just so we can take a look at that. It's going to take a lot longer to run. And I'm actually not printing out any displacement information down here, which you can see it's a little bit annoying. You don't actually know where it is. So that can be like a nice add. I probably would want to have some sort of printout at each of these points, just so I can know that the analysis is actually making progress. Maybe I'll pause the video and we'll come back when it's done running. Okay, a little bit later and we're done. Something that's really nice to see is that these are, and again, it's a little bit different because for load control, we're telling it a maximum displacement. So it's stopping at that maximum displacement, whereas with the displacement control, we give it the load protocol. But we can basically see that these curves are almost exactly the same. And we could, look at the data, we could plot these side by side to convince ourselves a little bit better, but basically what you want is them to be almost exactly the same thing. And here they are. And when I say almost exactly the same, I mean obviously up to the endpoints. Like if we had stopped this one here, we would we would see similar results. I will not run the Arclength control because it just takes a really long time to run in comparison to these past two. Again, I'm not as familiar with the Arclength control, so there might be some secret sauce that I don't know about that could be used to really speed up the analysis. I will say, with this pushover, this is a blisteringly fast pushover analysis. You'll see that if we run the code, it's like done really fast. So I was a little bit surprised at how much faster the pushover was compared to the cyclic analysis. I feel like there's probably something I haven't quite figured out there that could be used to speed it up significantly. Maybe if I go in to my load protocol and really refine the time steps just near these reversal points, that would probably be the thing that I would try to speed up. Then we can have a really big time step for a lot of these intermediate zones where convergence is a little bit nicer. But anyways, that would be my suggestion. I have found that it is running quite slowly right now, this Arclength method. Also, I just corrected a mistake. I realized that here I had accidentally passed in an extra variable to my analysis loop. So just a heads up, I've changed that from what it used to be. There used to be a deforcing here. Anyway, so that is cyclic analysis in OpenSees. So with this, you should have a really good basis, and I'll kind of zoom back out. Basically, between all the functions that are in here, I think you should have a really solid basis of functions to attack most problems. So we have load control of force, load control of displacement, both pushovers, and this cyclic analysis of load control. And then down here we have these displacement control functions, and then Arclength. So I think between these, that's a really solid basis. I hope these I hope these are useful for you to just pick up and use and modify to your own purposes. This is pretty similar to what I use when I do analyses these days. So yeah, I hope this is useful for you, and let me know if there's anything you'd like me to comment on below in the comments. And yeah, keep an eye out for future videos. I have, like I said, I'm not going to be doing as many OpenSees tutorials. I'm going to be doing more straight up programming tutorials in the future. But let me know if there's anything in particular that you want me to look at, and I'll do my best to get to it. Thanks.